So taking a look at our electrophilic aromatic substitution workshop. Couple names of compounds. This is anisole, that's benzaldehyde. So a couple of those compounds I asked you to know. Pretty simple stuff there. Here, I'm asking for the product of the reaction. So this is a halogenation. So one of the 4 types of electrophilic aromatic substitutions we learned. The product, if it's just a benzene ring, there's no directing group, so it's just putting one bromine on the ring. FeBr3 is a catalyst. You also make HBr, so the H that's here gets replaced with that bromine. Down here I asked for the mechanism for the activation of the electrophile, and that's shown here. All that needs to happen is the bromine lone pair goes to the iron. So the bromine lost electrons, so it has a plus charge. The iron has a minus charge now, formal charge. This makes this even more reactive. As you can imagine, a bromine with a plus charge can be reactive, but it's actually not this bromine that's reactive, it's the bromine next to it. So let's see how it reacts. So I ask you to draw the sigma complexes. So first you got to show the benzene ring reacting with the super electrophile. The pi bond reacts. The bromine next to the bromine with the plus charge. Alright, so that breaks that bromine-bromine bond. That's that addition reaction. It's going to form a carbocation, which we call these sigma complexes. But really, you can redraw them. It's just a fancy word for resonance structures of the intermediate. Just a term, doesn't matter. There's always at least 3. And essentially at this point you're just doing resonance structures, right? The pi bond moves between that bond, plus charge there. Pi bond moves between that bond, plus charge there. And you have your 3 sigma complexes. Now you need to go back and do the last step of the electrophilic aromatic substitution. The first step's addition. That's the slow step because it breaks aromaticity. The fast step's elimination because that reforms aromaticity. So the Fe minus, even though the minus charge is on the iron, it's the bromines that are electron rich. So the electrons between that iron-bromine bond take the hydrogen. We do that elimination, that kind of like E1 type, and we get our product, and we regenerate FeBr3 to get our product. So now let's take a look at a situation with a different super electrophile, but also with something, a substituent on the ring. So this is an electron donating group. So we could do resonance structures of this electron donating group. And what they're going to tell us is that in relation to this, the ortho and para positions will have a negative charge in some of those resonance structures. So that tells us where the electrophiles will go, either ortho or para. So I just drew one. I drew it as para here, and then I said also possible to be ortho. You know, both are possible. You just got to choose one. That's right. It's donating, exactly. Now let's draw those lone pairs in. It's donating because, right, those lone pairs are there. Yep, absolutely. So there's lone pairs on the substituent on the ring. If it's not fluorine, chlorine, bromine, or iodine, then it's electron donating. So yes, that's where it's going to direct because of that. But I didn't ask for that here, but it's good to clarify that. All right, so then I wanted to ask for the mechanism for the activation of the electrophile from number 5 above, not below. AlCl3, again, very similar to the halogenation. The chlorine here, the lone pair, goes to the aluminum, forms aluminum with a negative charge, chlorine with a plus charge. And then this carbon-chlorine bond just breaks. It can break, and you're going to form something like this. And you can draw a resonance structure where these electrons come down, and everyone has a full octet, and now this is sp hybridized. Right? There's just resonance forms to each other. Everyone has a full octet in this one, but it still tells you, this one maybe helps you understand which part of this molecule is electrophilic, is delta plus. It's actually the carbon. Maybe looking at this one, it's not as easy to see, but again, this is the carbon that's electrophilic, and you still have your AlCl4 minus. So now you got your super electrophile, have it react with your ring, take the pi bond, if I'm going to do it para, with the pi bond that's next to the carbon that's para to the group, pi bond reacts to the carbon, breaks the pi bond, that's that addition step. So now we've made a sigma complex, and again, I'm just showing here all these sigma complexes. So let's zoom in on the sigma complexes. And what you'll hopefully notice, right, there's the classic ones we've done. The pi bond moves, plus charge there, pi bond moves, plus charge there. But then there's a fourth sigma complex. There's always three, but here's the fourth. Because this electron donating, the electrons can come from outside the ring in, right? Now there's a plus charge on the oxygen. And of course people will be like, oh no, that's bad. But remember, the octet rule is more important. So actually this is the most stable sigma complex because everyone has a full octet. So this is part of the reason why electron donating groups are reactive, because they make stable intermediates, as well as making reactive starting materials, both things. So we come back up here, take that first sigma complex, and we do that elimination. Again, the aluminum has a negative charge, but the chlorines have all the electron density. The aluminum chlorine bond comes, takes the H, do the elimination, and we re-aromatize. We've also made HCl, and of course we've also regenerated AlCl3 as a catalyst. So you don't need to draw it here, but you could if you wanted to. All right, so I asked you to know four super electrophile generations. So we already did halogenation, which is the Br2. We did Friedel-Crafts acylation, which was adding the carbonyl, the C-double bond O. And then the last two are shown here. This is called the Friedel-Crafts alkylation. Again, do I care if you know Friedel-Crafts? Like, I just need to know the mechanisms, right? But we're familiar with those terms and see it. You're not afraid of those terms. So it's an alkyl bromide, a similar mechanism as before. Lone pair from the halogen, in this case bromine, goes to the iron. We make this bromine with a plus charge, iron with a minus charge, right? Bromine lost electrons, iron got them. We break the carbon-bromine bond, just like we broke in the first one, the bromine-bromine bond, same idea. So this time we make a carbocation. Of course, now if you make carbocations, you gotta be worried about rearrangements. So there's no rearrangement here, but that makes it super electrophile. Carbocations are really good electrophiles because they don't have full octets. And then here's a classic old one you've done, hopefully. Pi bond reacts with H+, pi bond's a nucleophile. You make a secondary carbocation. Carbocations can rearrange. So 1, 2, things that are 2 bonds away can do this is a methyl shift, an alkyl shift. So those electrons and that carbon, that CH3, move there and ends up right there. And now we have a tertiary carbocation. So right, carbocation rearrangements only will go downhill, so making something more stable. So like secondary to tertiary, or something with resonance is always a good thing too. But so these two involve carbocations, so then you gotta be aware of rearrangements. This one's the one that's kind of different, but we've done that before. And these other ones involve that lone pair from the halogen reacting with aluminum or iron or something like that. First step.